The last section we're going to cover this week is section 0.5, exponents and power functions. So we have some exponent rules that we need to look over. We're going to review these operations or rules for exponents that occur frequently throughout our textbook. So if we have a divided by b raised to the power of r, then we distribute that r to both the a and the b. For example, if I have 10 to the fourth over 5 to the fourth, I can go the opposite direction by saying, okay, I'm taking this version and taking it back to this one. So I can make it 10 over 5 all to the fourth. And 10 over 5 is 2, 2 to the fourth is 16. Not so bad. What happens if I have a fractional exponent though? This is what we call a rational exponent. So these are rational exponents. You don't need to necessarily know the term. It just means rational number is a ratio of two integers, aka it's a fraction. So it's a fractional exponent. And that's our way of showing roots. So if I have b raised to the 1 over n power, that means that I'm taking the nth root of b. So 5 to the 1/3, for instance, would be the cubed root of 5. What happens if I don't have a 1 in the numerator of my rational exponent? Then I have b to the m over n. Now reminder, m and n are both integers, they're both whole numbers. So it means I have the nth root still, but inside I have b to the mth power. This is the same as saying I have the nth root of b, the whole thing raised to the mth power. These two expressions are saying exactly the same thing. So what does this look like? For example, 5 to the 3 over 4 means still the bottom number is the root, so the fourth root of 5 cubed. Or you could also say the fourth root of 5, the entire thing cubed. What happens when I make this rational exponent negative? Well, when I make it negative, it means move it to the denominator. So now I have 1 over everything we had from the last example. So I have 1 over b to the m over n, or 1 over the nth root of b to the m, or 1 over the nth root of b raised to the mth power. What does that look like? 5 to the negative 3/4 would be 1 over 5 to the 3/4. Well, we already know 5 to the 3/4 could be the fourth root of 5 cubed, so we would have 1 over the fourth root of 5 cubed. Or we also know it could be 1 over the fourth root of 5 to the third power. We have a few more operations that we're going to be doing throughout our text with exponents, and these are more of a review of the type of properties you've already used with exponents quite often. The ones on the last slide were the ones that are the ones that might be a little less familiar, or maybe you've sort of forgotten what those are, but they're going to become important as we move through chapter 1 and we move through talking about power rule and what happens with rewriting square roots and cubed roots. These rules, however, these properties of exponents are the ones that you're probably so used to that you've forgotten when you learned all of these rules. So if I have b to the n, I am looking at b times b times b n times. So if I have 5 cubed, that's 5 times itself 3 times. If I had 5 to the fourth, that would be 5 times itself 4 times. If I had, let's see here, let's do 2 to the fifth, that's 2 times itself 5 times. Again, things you've probably already done. We're just writing them out very explicitly. If I have b raised to a negative exponent, much like we talked about on the last slide, that means I simply move it to the denominator. So if I have b to the negative r, it becomes 1 over b to the positive r. 4 to the 1 half, negative 1 half becomes 1 over 4 to the 1 half. We also know that 1 half means that's the second root of 4. We have a special name for second roots. We call them square roots. So that's really 1 over the square root of 4. So it's 1 over 2. What happens when I have two exponential expressions with the same base but different exponents and they're multiplied? Well, if they have the base stays the same, and we add the exponents. This still works even with rational exponents. So it doesn't work only when we've got, x squared times x cubed, and that becomes x to the 2 plus 3, which is x to the 5th. What happens if one of those exponents is a fraction? What if it's rational? Well, there's the cool thing. It doesn't change the property. We then would have, say, 6 to the 1/3 times 6 to the 2/3, which is 6 to the 1/3 plus 2/3. And if I have 1/3 and I add 2 more, they add up to 3/3, which is 1. So I just get 6 to the 1, which is 6. Likewise, if I were to have, say, x to the 3rd over x, well, that x technically has a power of 1. We know then that would become x to the 3 minus 1, or x squared. Does this change when we have rational exponents? And the answer is no. 7 to the 4/3 divided by 7 to the 1/3 becomes 7 to the 4/3 minus 1/3. Same property. 4/3 minus 1/3 is 3/3, which is 1. So we end up with 7 to the 1, which is 7. So now what if I have a base raised to a power raised to another power? This is where I like to think of it as a video game where you're powering up, so you're getting 2 times, right? Or you're getting 10 times your multiplier for your points. So what happens is when we have an exponent raised to an exponent, we're powering up, we multiply them. So again, we could think of this as x squared cubed. That's the same as saying x squared times x squared times x squared, or x to the 2 times 3, which is x to the 6th. Same thing can happen even if we have rational exponents. 4/5, 9 to the 4/5 raised to the 5/8. Well, then our property says, oh, just multiply those two exponents. Okay, cool. So I'll multiply the 4/5 times the 5/8. And then something nifty happens. Those 5's cancel out. And I'm left with 4 over 8, which is 1/2, which is a square root. So we end up with a square root of 9, which is 3. Our last property here says, what if I have a times b and the whole thing is raised to the r? Well, that's the same as saying a to the r times b to the r. So I could have xy to the 4th. That would be the same as x to the 4th times y to the 4th. But it also works in reverse. If I had, let's see here, let's think about it as x cubed, y cubed, I could also write that as xy quantity cubed. It works both directions. And in this case, the example I gave you was 125 times 27, the whole thing to the 1/3, which means I'll distribute that power to the 125, multiplied by distribute the power to the 27. 125 to the 1/3 is the cubed root of 125, which is 5. And the cubed root of 27 to the 1/3 is the cubed root of 27, which is 3. So we end up with 5 times 3, which is equal to 15. Let's try applying some of these properties. So 25 to the 1/2 is the same as saying the square root of 25, which is just 5. Not so bad. If we look at 27 over 8 and we raise that to the 1/3, remember that means we're going to take the power in to both pieces. So we end up with 27 to the 1/3 over 8 to the 1/3, or the cubed root of 27 over the cubed root of 8. Now here's the other cool thing is you can evaluate these in your calculator. If you wanted to do that, you would do 27, you would hit that caret button, and then in parentheses, you would put 1 divided by 3. And it will give you the same thing. Cube root of 27 is 3. Cube root of 8 is 2. So you could actually put this entire expression into your calculator and then use that, our favorite, math enter, enter, to get the fraction back, which would be 3 over 2. I'm going to show you how to do these by hand, but the first 1, 2, 3, 4 of these you can do even in your calculator without having to do them by hand. But it's good practice to do them by hand because you're going to have to do some of this stuff here and there on your homework and on your exams. So showing work is always good because then I can help you figure out what went wrong, because if you forget your parentheses in your calculator when you do a fractional exponent, things don't go the way they're supposed to. So we'll see that a little bit more when we get into some applications of these properties. If I do 1 over 64 to the negative 2/3, then when I distribute, I end up with 1 to the negative 2/3 over 64 to the negative 2/3. So here's the cool thing here is that 1 to any power is just 1, but that 64 to the negative now comes up. So it's 1 times 64 and now becomes positive, the 2/3. That's the cubed root of 64, right? Squared. The cubed root of 64 is 4, so we end up with 4 squared, which is 16. And again, this is something you could put into your calculator. How about one more? With these are the types that you can put into your calculator. We have 4 to the 1/3 times 250 to the 1/3. This is one of those ones where I explained before, you can actually go backwards. So this came from 4 times 250 all to the 1/3. Well, 4 times 250 is 1,000. So 1,000 to the 1/3 is a cubed root of 1,000, which is 10. Where some of this can get a little trickier is when we look at expressions that also involve variables. But here's the thing, the properties still hold true. So if I look at these in different groups, I could look at negative 25 over 5, and then I could look at the x to the 7th over the x squared, and then I can look at the y to the 9th over the y cubed. So let's do them in that order. Negative 25 divided by 5 is negative 5. X to the 7th over x squared is x to the 7 minus 2, and y to the 9 over y cubed is y to the 9 minus 3. So my final simplification here becomes negative 5x to the 5th and y to the 6th. So it looks kind of ugly, but it's not so bad. Likewise, if we look at x to the 36th, y to the 12th, all raised to the 1/6, our property here says, well, bring in the 1/6 and multiply it by the other powers. So I get x to the 36, oops, not 3 over 6, sorry, 36 times 1 over 6 times y to the 12 times 1 over 6. So I get x to the 36 over 6, y to the 12 over 6. Well, 36 divided by 6 is just 6, and y is now 12 over 6 is 2. So we end up with x to the 6th, y squared. But how can we apply these properties? Well, let's start with simple compound interest. If you invest a principal amount P, in other words, this is the amount you start with, your principal P is the amount invested at the beginning. and you compound it at an interest rate of I per interest period for a total of n interest periods, the compound amount A, so we call that the compound amount, that's also the same as the accumulated money, right? So why I like calling it A is for accumulated. It's how much you have of the investment plus the interest that you've earned. At the end of the nth period, it will be A equals P times 1 plus I all to the n. So if you invest $7,000 at a 5% interest per year, with interest compounded annually, how much money will you have after 10 years? Well, here we started with our principal P of $7,000. Our interest rate I is 5%. But here our interest rate needs to be in decimal form only. So we need to divide it by 100 to make it into a decimal, so 0.05. And then n is 10 years. So all we have to do here is plug this in to the formula. We have A is equal to P, which is 7,000, times 1 plus 0.05 to the 10th. And this is easy enough to plug into your calculator. You can do it just as it's written, or you could do it as 1.05, then raise it to the 10th, and then multiply it by 7,000. And what you'll find that you have after 10 years is you'll have $11,402.26. And I know I was asked about rounding. This is about money, so it's always to 2 decimal places. So what happens if we have interest compounded more than just annually? The last formula was only for annual interest compounding. Now what happens if I compound my interest maybe, I don't know, monthly or 12 times a year? Let's see here, yearly would be 1 time a year. So M in this case is the number of times that our interest is compounded per year. So P is still our principal amount, or the amount we invested at the beginning. R is still our interest rate as a decimal, right? Only as a decimal. But now we have this M that we've included that wasn't in the last formula. But here's the cool thing is if we let M equal 1 and compound it annually and plug this into our formula, we end up with A equals P times 1 plus R to the T. This is exactly the formula that we had on the last slide. This formula is exactly the same as the last one. So if you're writing down formulas to keep track of for an exam, this is really the only one you need, because if your interest is compounded annually, M just becomes 1 and you're back to the same formula you had before. But what if M is, well, we already said monthly means that M is 12. Yearly means it's only 1. Let's see. Well, remember, yearly is also annually. That's another way to say it. What if we said weekly? Well, there are 52 weeks in a year, so M is 52. If we said daily, we have 365 days. Now, I know this is a little different, perhaps from another business class you've taken, because I know that banks, when they say daily, they use 360 to account for holidays. It'll be very, very similar in the end, the amount of money that you're getting in the end, but not exactly the same. And I will say that Pearson is expecting 365 and not 360. So if you've gotten in the habit of using 360 in your business courses for measuring interest in this way, just know that Pearson's expecting 365. If you use 360 on an exam, I won't take off for it, because I understand that it can be difficult sometimes to switch, if you've been doing 360 all this time, and then to switch it to 365 can be a little, you might forget in an exam, and that's okay. So how do we apply this formula? Well, let's see here. We're going to invest $1,000 at 8% interest per year with interest compounded monthly. So how much money will we have after 2 years? So not 2 years, 5 years. So our P here is still what we started with, which is 1,000, our principal. Our interest rate R is 8%, which again, as a decimal, divide the 8 by 100, you get 0.08. Interest is compounded monthly. And how many times does a month happen in a year? 12. So M is 12. And how many years are we leaving it invested? T is 5 years. So if we plug this into our formula, A equals P, which is 1,000 times 1 plus R, 0.08, over M, which is 12, to the M, 12 times T, 5. Plugging this into your calculator can be really challenging. So my suggestion is that you find the pieces and you do, say, 1 plus 0.08 over 12 and find that number first, or in this case, 12 times 5 is 60. You could plug it in exactly this way on your calculator and still be fine. And if you do plug it in, what we're going to find out is the amount of interest after 5 years added to what we started with is $1,489.85. So now that we've finished section 0.5, you can finish both the online homework number 1 and homework number 2.